All right, good morning, everyone. So I hope some of you were able to enjoy the break yesterday. I know that a few of you were at a conference giving presentations. So a few reminders that I am waiting for your selection of seminars so that I can then distribute the seminars based on preferences. Hopefully, as I said, I can accommodate your top preferences, but at the minimum, I will definitely get one of your top preferences as one of your actual presentations. All right, so that's due next week, the selection of the seminars based on your preference. Another recommendation is that now that we know the teams for the manuscript, that you guys should start to communicate with one another virtually so that you can distribute the topics that you're interested in working on. And obviously, I do suggest that there's overlap. So I do suggest that several of you take a few subtopics so that you can read similar manuscripts and be able to share and communicate your ideas. So that's an expectation, especially given that these groups are fairly big for the material. All right. So what we're going to do today is begin basically what's going to be a two-part lecture. This first part would be more lecture focused, and then the second part, which would be on Thursday, will be on the literature that I've asked you guys to read. Some of the material today is actually taken from the actual textbook. Thursday, there will be more of an interaction with you guys, and so that's one of the reasons why I've asked you to write up an assessment of one of the articles of your choice that I have provided you. All right, so let's go ahead and get started. All right, so we're going to be focusing on this idea of the balance of metal ions in the body. And I've put this in quotation marks because we're not necessarily talking about balancing exactly, but what happens when you lose control of that balance, when you lose control of, let's say, the homeostatic levels of metals. So let's quickly review the topics from our previous lecture. We defined metallomics, which to an extent can be seen as a study of the aqueous speciation of metal-containing species. But in this context, we're really looking at the localization of metals and what role certain metals play, especially as they are really important for the function of different components of the omics world. We explored considerations that are important for the extraction and purification of biomolecules, especially metal-containing ones. So we looked at conditions very briefly that could affect the covalent interaction with metals. We identified some elemental analysis approaches that can be used to examine metal-binding biomolecules, and I briefly introduced X-ray absorption spectroscopy to give you more information about electronic transitions, at least from the perspective of certain elements that one can take advantage of in order to explore metal coordination. We're going to now focus on metal ion homeostasis and regulation, but again, this is not specific to essential metals, but that is going to be our starting point. So essential metal ions play a wide range of roles as cofactors or coenzymes for the proper functioning of enzymes. So synthesis and breakdown of nucleic acids and the production of lipids and carbohydrates. Obviously, there are much more that metals can actually do, and these being some of the highlights. Several non-essential metal ions can aid in these processes in a therapeutic manner, meaning that they may be able to supplant some of the essential metal ions, but that they themselves are not necessarily required for our survival. So to deliver the correct levels of these metal ions to biomolecular mechanisms that depend on them, there exists a network of metal chaperones, trafficking proteins, and storage reservoirs to maintain optimal metal ion equilibrium. And to an extent, we have talked about this using specifically iron as our perspective of a metal that gets trafficked or that gets transported, and that transportation process helps to maintain it soluble, but also helps us to maintain it bioavailable. Then looking at the trafficking of that metal for storage, but also for functionality. What we're going to focus on in terms of concepts about the loss of balance is as follows. Often, when the internal homeostatic environment breaks down, the body operates in an aberrant manner, characteristic of a disease state. Sometimes the body intentionally disrupts the metal ion equilibrium in a defensive manner. Non-essential metal ions can be employed to help restore balance to disrupted processes, but their levels must be tightly regulated. And that last node is actually true even for essential metals, this idea of controlling the levels. So today, we're going to look at a specific case study that highlights the component B that I've listed here, this idea of the breakdown of homeostatic control over the levels of certain metals and how that can lead to a disease state. So the disease state, so we're looking at this as a case study we're going to focus on is Alzheimer's disease. So this particular disease is part of the class of disease of dementia. It is a neurodegenerative disease diagnosed in individuals mainly greater than 65 years. So some of the symptoms characteristic of the disease: progressive loss of memory, senses, and bodily functions. So as an example, incontinence. In later stages, patients experience difficulty speaking and eating. They lose the ability to respond to their environment. And this is a disease that can be fatal, or that is fatal. It affects approximately 24 million people worldwide, and this is actually expected to triple by 2040. So from the point of diagnosis, typically what has been seen is that death occurs 8 to 12 years. So current statistics: number 5, global leading cause of death. Number 4 in Puerto Rico. I say I misspelled Puerto Rico there. I'll fix that. All right, just want to give you an overview. So I am not an expert in the brain, but just to give you a perspective of what is actually getting affected in the brain, so that you can see the difference between a healthy brain and a brain that is affected by the disease. So just here are the 4 major lobes of the brain. I'm not going to go into any detail here. Another important features are the ventricles. And so here you get a perspective of the brain, the ventricles, and the cerebellum. All right, so what are the physiological features of Alzheimer's disease? So in this cartoon representation, we have one side, the left side, that's representing what is a normal brain, versus the right side, which is representative of an Alzheimer's brain. So we're focusing on brain cells, so looking at neurons as an example. Okay, so this is a depiction of what would characteristic of a healthy neuron versus what you see to the right. You see these neurons, and they're basically experiencing stress. They're experiencing atrophy. You actually see that the tissue, compared to the normal brain, it has gone a lot of loss of mass. Right. When you focus on the environment of the neurons, you see these 2 major populations. One of them is the amyloid plaques, and we're going to talk about that. And another one is these neurofibrillary tangles that are formed due to a protein that becomes phosphorylated extensively. All right, so we're going to talk about these particular features and how they lead to this progression that ultimately leads to death. All right, so here is a schematic that gives you more of an insight as to what's actually happening. So those amyloid plaques that are forming, initially, they're coming from a protein that's located in the membrane of the neurons. And so the protein has undergone a proteolytic degradation. So all proteins go through this process. So the control of proteins is like you have to have them degraded, and then the peptides that are then formed are utilized or are disposed of. What's happening here, and we're going to look at this a little more closely, is that those degradation products can lead to the formation of these structures known as plaque. And so we're going to talk about, well, what exactly is the constituents of the amyloid plaque? To the right, we're looking at what's happening with this protein, the tau protein, in terms of its formation of these neurofibrillary tangles. So again, this protein, something about it is becoming dysregulated, such that you get this extensive phosphorylation that leads to the formation of these particular structures. Right? So these structures ultimately lead to the progression of the oxidative stress that these neurons can experience, and it can actually lead to cell death and the atrophy. So here I'm showing you a magnetic resonance image of brain extracted subjects. And so we're looking at to the left, the image of a brain from a healthy control subject. So this is someone who is 85 years old versus the brain to the right from an Alzheimer's disease patient, male, 78 years old. And so there,
Excuse
go
me,
ahead.
I don't know if this is happening to the other students, but I can't see the magnetic resonance images in the presentation. Like, I can't see it on the screen.
Oh, I can see it on the screen. I
I
have
can see
to.
them too.
You can't? Oh, you
Okay,
can't.
then it's
I
a me problem.
can.
Um, Quick question, guys. Are you using Chrome? Because typically Google Meet has been working much better using Chrome than other browsers. So if you're not, my suggestion is to switch over to Chrome. But I can definitely see the images.
I can see them now, thank you. I think it was my internet that just wasn't working very well.
Oh yeah, I'm sorry about that. Okay, so to the left, where we're looking at is a magnetic resonance image of a healthy brain. And the choice of the subjects are so that they're reasonably comparable in age, right? So you can expect differences between someone who's younger versus someone who's older. But as you can see, in terms of the actual composition of the brain, the Alzheimer's disease patient, you see evidence of tissue atrophy. You can see that those ventricles are now enlarged. All right, so these are features that are characteristic of Alzheimer's disease. And the thing about Alzheimer's disease is that it's actually very difficult to diagnose, right? Oftentimes, the true determination that someone had this disease is, after death, being able to actually examine the brain matter. So it's quite a difficult disease to get a hold of. You do have other types of dementias that complicates the particular diagnosis itself. So the reality is there is no cure for Alzheimer's disease. Uh, and in part, this is because the true understanding of what is the onset of the disease is not clear. So at present, existing treatments focus on helping people maintain mental function and manage behavioral symptoms while slowing down the symptoms of the disease. So currently, there are several FDA-approved drugs. So we can classify them in terms of when they're applied to a patient. So for people that are the early and middle stages of the disease, you have this cholinesterase inhibitor drugs that help to slow down symptoms, namely memory loss, and help to regulate thinking. So basically, you're trying to slow down the progression, but the progression is going to happen. For later stage patients, you have these N-methyl D-aspartate antagonist drugs that are palliative. Okay, so palliative basically means that they're just trying to improve quality of life. They're at this point, you're not really slowing down anything. You're just trying to make life reasonable for these people. So you help people to maintain certain daily functions. So here, what I'm going to present to you is a series of hypotheses as to not necessarily the onset of the disease, but really some of the things that have been observed that could be correlated to the onset, or these could be the products of the disease already in progression. Okay, so that's just to not to mislead you to say that these are hypotheses as to the actual cause of the disease. So again, the biological cause is unknown. I mean, there are many strong hypotheses to why that's the case. And I would say this one that I'm going to show you right now is probably one of the lead ones. All right, so Alzheimer's disease is believed to be caused by the formation of insoluble senile plaques, mainly in the temporal lobes of the brain, which are important for memory function. So here I present to you a representation of what is going to lead to the formation of these plaques. So again, it starts up from this protein that's located at the membrane of the neurons, our brain cells, the amyloid precursor protein. So what is essentially happening is that you have this protein that's breaking down during a proteolytic process, and so you get the formation of these peptide products, okay, and they're forming in the extracellular region, so outside of the cell. And so you have these two principal peptides, A beta 40, A beta 42. These amyloid beta peptides, that's what typically they're referred to. And so it is propose that these two peptides are really important as to then the formation of the plaques. And so here you see the sequences. They're basically the same peptide. They're coming from this protein, just that one is 2 amino acids longer than the other. All right, so let's talk a little bit about the features of these peptides and how they can potentially lead to the formation of the plaques. So A beta 40 is quite soluble, whereas A beta 42 is insoluble. So that 2 amino acid difference is quite significant. The peptides self-associate at the sequence LVFFA. So here it's underlined and for both of these peptides. Okay. And so it is believed that because of that self-association, all right, that leads to the transformation of these peptides into these higher ordered structures. So imagine thinking of the peptides as these monomeric species, then they're becoming affiliated with one another, leading to an oligomerization process that then can extend itself into these higher order structures that are the protofibrils and then finally the fibrils. Right? So leading to these formations that will be known as the plaque. But there are additional features. For instance, the A beta 42 monomers can self-associate by forming two in-register parallel beta sheets. So if you guys have taken biochemistry, you'll be familiar with this particular feature of the secondary structure of proteins. The orientation of these peptides or these amino acids in such a way that you have the formation of these sheets that can be in a parallel and anti-parallel fashion. Here you have them depicted in this parallel fashion. Well, this is technically the single peptide. So you see the amino acid 42, and over here, at least depicted in this cartoon, you have the L17. So that is the group. Remember, there's that 5 amino acid group that can self-associate, but here what you're seeing is this particular monomer in itself self-associating in such a way that you have an arrangement of that monomer with other monomers forming this structure beta sheet. Okay, so you have this beta sheet right here, then you have this turn, and then you have this other beta sheet. Okay, so this is the type of motif that the A beta 42 can adopt. But added to this idea of the fibrillation process, just via the peptides themselves, has been the hypothesis that metals can play a role. And so what has been observed is that there's been elevated concentrations or even perturbed biodistribution of copper, copper 1, copper 2 plus, iron, iron 2, iron 3, and zinc. And so that perturbation or the elevated concentrations of the metal within these structures is believed to be very significant. This hypothesis, the metal ion hypothesis, suggests that metal binding to A beta influences the conformation of the two peptides and facilitates their incorporation into fibrils that form the plaque. All right, so here, the even larger order structures, the proposal is that metals are contributing to that. So you have this component right here. So because of this hypothesis, people have tried to understand, well, what about metal binding is contributing to these higher order structures? Because remember, metals have coordinating, they're able to coordinate to different biomolecules. So perhaps that process of coordination can bring these structures into close proximity, right? So they'll interact with the metal center, and then that can lead to these much greater structures, these plaques that are forming. So what people have tried to do is understand on a very fundamental level is the ability of the peptides to bind metal. And so, so self-association of A beta peptides is easy and rapid. And because of that, it becomes quite difficult to study metal binding because you already have these peptides that can aggregate and form these complex structures. That trying to understand their interaction with metals becomes quite complex, especially if you're thinking about tools that you can use to understand the coordination. When you already have these really complicated materials that may no longer be soluble, then you start to lower your tool set of what you can use to try to understand metal coordination. So, sometimes you can try to overcome this by using low concentration of peptides to minimize aggregation. but then you're pushing the limits of detection of techniques that are sensitive to metal and metal coordination. So there are additional things to consider that make this even more complex. So peptide association results in flexible polyfunctional ligands that, although contain standard metal binding residues like histidine, their interaction with metals can be complicated to study due to things that we're already aware of, the influence of pH. So we have seen how pH can dramatically affect interaction with metals. Well, we have not mentioned this, but you guys probably have seen this in analytical chemistry, how ionic strength, so salts, can influence interaction between different species. And even the nature of buffers can play a major role in terms of being able to get a gauge as to how metals may be able to interact with these peptides, given that buffers, to an extent, even have metal binding capacity, so that can add a layer of complexity to these studies. So um, as you can expect, trying to work with these A beta peptides as they are can be very difficult, and it can lead to widely diverse binding constants and structures. So if you want to just get a general understanding, what people have done is to try to simplify. Okay, and so simplification in this context means, well, why not just work with smaller forms of the peptides? Because just to get some fundamental understanding about the complexation process, and also very importantly about once a metal is complex, how that might be able to influence the chemistry of the metal. All right, so what we're going to do here, we're going to focus on some studies that have been done in terms of the coordination of certain metals with a truncated peptide, the A beta 16 peptide. And so we're going to focus first on copper, and we're going to look at copper 2 plus first. So if you were to determine the electron configuration of copper 2 plus, that would be 3d9 case. And so d9, we're one electron away from saturating all of the d orbitals. So copper 2 plus, in terms of our perspective, hard, soft, acid base, this one falls in the range of an intermediate metal. As such, it has pretty flexibility in terms of the type of interaction that it can have with different coordinating moieties. Copper 2 plus can form 4 coordinate structures, 5 coordinate structures, 6 coordinate structures. So here I am a little bit more specific about geometry. You can have an sort of a distorted octahedral geometry on these tetragonal structures. I'm not going to go into the rationale as to why. So if you take a formal inorganic chemistry course, you will become aware of what is known as a Jean-Teller effect. That's very a characteristic of copper 2 in a 6 coordinate environment that leads to these distorted structures. But so copper 2 plus D9, well, that results in one unpaired electron, and that one unpaired electron is actually quite valuable in terms of techniques that can be used to probe the coordination environment of the metal. It's paramagnetic, and so a really important tool that you may not be familiar with, but at least to orient you as to the utility of this technique, electron paramagnetic resonance, abbreviated as EPR, is basically the electron equivalent of nuclear magnetic resonance, where in that technique we're looking at the nuclear spin of certain elements that have this that you can actually take advantage of this particular feature. Here you're focusing on a metal center that is paramagnetic, and so you're able to track the environment of how that paramagnetic center is affected by its coordination. It can be quite useful in understanding how a transition metal, is coordinated. So in fact, EPR has been used to get an understanding of how copper 2 plus is coordinated to this truncated peptide, this A beta 16 peptide. And so here we get a depiction of the coordination of that copper. So I'm going to ask you guys, looking at that copper, what would be the coordination geometry? So you can type in the chat, you can get into your microphone. What is the coordination geometry of that copper? So I see one response there. I see a square pyramidal, another one square pyramidal, and that's correct. It is square pyramidal from this perspective here. So you have the these 4 atoms coordinate into the metal, forming that square structure, and then you have this axial ligand formed by that oxygen. All right, so where exactly are these coordinating atoms coming from? So we have that aspartate, number 1, so the beginning of the peptide, is actually contributing quite a bit to the coordination of that copper. You have the amino terminus serving as a coordination, so the nitrogen from the amino terminus is serving as a coordinating atom. You have coordination through the side group right here. It's a carboxylate side group. The aspartate is a carboxylate containing amino acid. And you also have coordination through the carbonyl oxygen that's coming from the aspartate. So that single amino acid is contributing 3 coordinating atoms. Then you have coordination via histidine 6, and then you have coordination via another histidine, either histidine 13 or 14. All right, so just to give us a perspective, and this was what was observed at a pH of 6.5. So this is a pH-dependent speciation. All right, so what happens when you look at a pH of 9? So we went from something that was close to neutral to now to the basic range. All right, so we see a similar coordination geometry, so square pyramidal, but we see a little bit of a difference in terms of the coordinating atoms. So the aspartate still contributes the amino group, it still contributes the side group, carboxylate, but then you see there's a bit of a change in terms of the backbone of this peptide, where instead of the carbonyl oxygen from the aspartate coordinating to the copper, you have the amide nitrogen. That nitrogen is coming from alanine 2, okay, and that's coordinating to the copper. So that amide nitrogen has, from this perspective, has become deprotonated, possibly facilitated by the pH and also the presence of the copper, and able to coordinate to that copper center. Then you have coordination from this other carbonyl oxygen, and then you have the histidine over here coordinating. So you have these different groups. So you have a similar coordination to the copper, same coordination geometry, but differences in terms of which, a few differences in terms of which coordinating atoms are interacting with that metal center. And it turns out that at a pH of 7.4, so there's a pH that would be, let's say, of typical biological fluids, let's say blood, the speciation is a mixture of the pH 6.5 and the pH 9 structure. All right, so that gives us a perspective of how copper can bind to these peptides, copper 2. Well, now let's consider what happens when you have copper 1. So now copper 1, electron configuration is D10. So you've saturated all of your d orbitals with electrons. Copper 1, from our perspective, is a soft metal, right? So that 1 electron difference changes copper from intermediate to soft. So typically for copper 1, we see coordination environments that are for 2-coordinate or 3-coordinate. And the addition of that 1 electron now transforms the copper into a diamagnetic species. So typically when you're working with diamagnetic metals, you're able to exploit proton NMR. I will say that there is a complexity with working with paramagnetic molecules when trying to do proton NMR or typically NMR experiments, because what happens is you lose some of the resolution. You can do it, but you lose some of the resolution that is characteristic of proton NMR. That's why many people use proton NMR, because of the wealth of information that you can get in terms of the protons that are present in your molecule. All right, so here is a depiction of the coordination of copper 1. And so you can immediately see the difference, right? You have a much lower coordination number. Again, the copper is soft in this context. So you have the contribution of coordination from histidines, histidine 6, histidine 13, and histidine 14. All right, so you get this equilibrium between these two structures. This 2-coordinate structure to the left and this 3-coordinate structure to the right. And so this, let's say that this equilibrium exists throughout the physiological pH range. So by that I mean this range that we were focusing on of a pH of 6.5 to 9. So you get a mixture of these structures. All right, so here we've gotten a perspective of the copper coordination, Well, what about zinc and iron? All right, so let's focus on zinc. Again, in our perspective of the type of metal that zinc is intermediate. It's uh, D10, just like copper 1 is, but it is an intermediate Lewis acid. So it does form different types of structures. You can have four coordinate tetrahedral structures, quite common for zinc, five coordinate structures. So you often will see zinc playing a role in catalysis or in enzymes, and you see a fluctuation of coordination numbers from 4 to 5. And then zinc 2 plus can also form six coordinate structures. Because it is D10, it is diamagnetic, so it allows for studies to be performed by proton NMR. When we're talking about iron 2 plus, well, that's D6. Okay, and so when you're at D6, you have two possible arrangements of those electrons depending on and so here, the low spin and the high spin, I would say that these terminologies are specific to a coordination number 6. I don't want to mislead you into thinking that that's going to be true for any coordination number. But I'm highlighting that because iron tends to really form a predominant six coordinate structures, although there you can definitely find four coordinate structures, tetrahedral structures for iron. All right, but iron 2 plus, D6, when we're looking at coordination number 6, then you have the two possibilities depending on the delta octahedral. You can have the extent of low spin, so an S equals to 0, and S equals to 0, then you basically have something that is diamagnetic. But then if you have the high spin representation of iron 2 plus, well, that would be S equals to 2, and so that would be paramagnetic, right? So depending on the coordination environment, you can have a dramatically different result. So iron 2 plus, again, can form structures of this nature, 4 coordinate, 5 coordinate, 6 coordinate. And you can exploit proton NMR, EPR to understand the coordination of iron. All right, so we're going to look at how this truncated peptide may be able to coordinate to these metal ions. So here we're looking at the coordination of zinc 2 plus, and so we see already a difference of what we observe for copper 2 plus, and definitely a difference what we observe for copper 1 plus, where this zinc 2 plus is we're in a 5 coordinate environment, and that appears to be something that's more like a trigonal pyramidal structure, okay, or a trigonal bipyramidal structure. And so I would say that is actually distorted. And so we can look at the features of what's coordinating to that metal center. We have the aspartate amino group. We have coordination from histidine 6. We have coordination from the side group carboxylate of the glutamate 11, and then coordination from histidine 13 and histidine 14, such that the histidines are constituting the equatorial plane, and then the amino group from the aspartate is in the axial position, and the carboxylate is from the glutamate 11 is in the axial position. All right, so I would say that it's been observed that this type of structure predominates in the physiological pH range. For iron 2 plus, there are some differences, but for the most part, a lot of comparisons to zinc 2 plus. So iron 2 plus falls in the category of something that would be intermediate as well, as far as the Lewis acidity characteristic. So here we have, again, something that is trigonal bipyramidal in terms of its geometry. And we have the coordination of the 3 histidines in the equatorial plane. We have a carboxylate group from glutamate, but this glutamate is glutamate 3. Okay, whereas in the zinc structure, what was observed was the glutamate 11 that was coordinated, providing that side group. And then you have the aspartate carboxylate, the side group of the aspartate, coordinating to that metal center. All right. It's not always easy to understand exactly why you have these, I would say, subtle differences, but you have to think about the contribution of the ionic radii of these metals and how that can really have an impact in terms of the affinity to certain moieties. Okay. It's believed that the iron 3 plus exhibits a speciation that is comparable to the iron 2 as far as its coordination to the A beta 16 truncated peptide. All right, so this was just to give us a perspective in a simplified manner as to how these metals might be able to coordinate to the A beta peptides. All right, so now there's this added complexity, what is known as the oxidative stress hypothesis. So according to this hypothesis, the metallated A beta peptides facilitate the production of reactive oxygen species and even reactive nitrogen species, right? So adding the metallation component not only can lead to these higher order structures, the plaque formation, that's what people have proposed, right? But also the coordination of the metal in these environments can exploit, when we're talking about copper and iron, their ability to engage in redox actions, a reaction. So we're looking at the redox activity of these metal ions. And so to the right, we have just a cartoon representation of how these proposed metallated peptides can lead to the transformation of oxygen into the reactive oxygen species. What has been observed post-mortem, so analysis of Alzheimer's disease brains, is an abundance of oxidized lipids, proteins, and DNA bases, basically the hallmarks of oxidative stress. So to an extent, I would even propose that perhaps, and I haven't actually looked at this literature, so something that would be worthwhile for all of us to look at, is that perhaps we're looking to an extent, if from the perspective of iron, a form of cell death that is part of what is known as ferroptosis, right? And that is a type of cell death that is iron dependent, and that is actually distinct from the apoptosis, which is a form of programmed cell death. All right, so let's look at this more closely. And I'm going to focus on ROS generation, so the reactive oxygen species, from the perspective of copper. The very same schematic that you see here can be proposed for iron 2 and iron 3, is what has been observed. All right, so we're going to look at the different steps here. I don't want to just gloss over this because that's what people typically do. They say reactive oxygen species and then let's move on. I just want to look at this a little more closely so we can see a little bit about the movement of electrons. So in this first step here that you see, this metal reduction, you're looking at copper 2 plus becoming reduced by 1 electron forming copper 1. And if the cellular environment is highly copper 1 based, right? So copper 1 is quite redox active. Both copper 2, copper 1 are redox active. You have this interconversion. All right, so here in line number 2, okay, we're looking at what is the formation of superoxide. All right, so let's look at that. So we have copper 1 interacting with oxygen, molecular oxygen. So when you're thinking about the charge, right, there's going to be a really important component here. The oxygen in molecular oxygen, each one will have a charge of 0. Okay, and then we're looking at the copper having a charge of +1. Okay, so let's track that. But then on the right, what we have is we have the copper having experienced a loss of 1 electron. Now it's copper 2 plus. So where has that electron gone? Well, that electron has gone to the oxygen, okay, and it has formed, because of the addition of 1 electron, it has formed a radical which has a negative charge. All right, so now this has a 1 minus charge. All right, so from this perspective, this reaction is balanced in terms of your charge. All right, so look at the next step, the formation of hydrogen peroxide. Okay, so here what's happening is now that superoxide species that was generated by the copper 1, well, that goes on to react with protons. And what is it doing? It's generating hydrogen peroxide. All right, so let's track this. So here we have the proton, right? Each one is +1. Each one of the superoxide is -1, and then we have two of these and two of these. Okay, so I think you guys can follow along with that one. Then if you look at the right, the oxygen, as we know, each one of the oxygens is a charge of 0. I'm just putting 0 just to represent the overall molecule, but it's 0 per oxygen. But then if we're focusing on the hydrogen peroxide, all right, so this is something you would have learned in biochemistry, the following the charges of the different atoms. So here, we're looking at the hydrogen part. Each one of those hydrogens has a charge of +1. But the peroxide, that has a charge of 2-. Okay, so then we can see where there is a movement of the electrons here, where you can see now that the peroxide group has picked up, this group here has picked up an electron, and that electron, to an extent, has been from one of the actual superoxides, right? So remember, you have two equivalents of superoxide. One of them gets converted into molecular oxygen, the other one gets converted into the peroxide group. The peroxide group is 2-. Okay? And if anyone knows hydrogen peroxide is indeed a radical. All right, let's look at the next one. The next one is known as a Fenton reaction. So that is the reaction of a metal, in this case copper 1, interacting with hydrogen peroxide, yielding the formation of the copper 2 plus, the hydroxyl radical, and hydroxide. Okay, so we can do a similar type of comparison. So you have +1 copper, you have 2-, the peroxyl group, you have the two hydrogens. Okay, you have the copper 2 plus. Okay, and then you have now the radical, the hydroxyl radical. So here, it gets a little bit tricky to see because that hydroxyl radical is actually neutral in charge, the molecule, but you can break it down into the components. +1 for the hydrogen, the oxygen is -1, okay? And then over here, for the hydroxide, well then the hydrogen is +1, the oxygen is 2-. Sorry about my inconsistency of where I put the charge, minus before, after number. In this context, it doesn't really matter so much, right? Well, you get to see here that where there is actual, the movement of the electrons. So what's happening here? Well, what we can see is you're getting a disproportionation of the hydrogen peroxide, so that O2 group is now forming the hydroxyl radical and forming the hydroxide. So that that now is another reactive oxygen species. Okay, next is the Haber-Wise reaction. So here we have our superoxide, right? So that is going to be present here. So that's your -1 group overall. Then you have your 2-, okay, and so forth. I'm just keeping track of what I have here. Okay, and this is 0 over here. Okay. All right, next, and this is a really key one, is this hydrogen atom abstraction. Why is that key? Well, why that it's key is because we're now looking at an organic molecule that's interacting with this hydroxyl radical, okay? And then that's leading to the organic molecule becoming a radical. All right, so let's look at that. So the R group, basically that would be a carbon interacting with a hydrogen. Again, this is something you would have learned in biochemistry. So then this would be +1. And if we're looking at the R as a carbon, okay, this would be -1 over here. So here, this would be -1, +1. All right, this is now 0, this is 2 minus 2 protons. There you go. Okay, so you see that the oxidation state of the carbon has changed. All right, and now what you have here is now something that is quite unstable. So thinking ahead, what is this organic molecule? Well, we're talking about this happening within the cellular environment. So this can be anything that is basically organic. You can think about this as being a biomolecule, protein, so forth. And so this is a process that metals can facilitate, these formation of these reactive oxygen species that can go on and react with biomolecules and dramatically transform them to such an extent that basically they become not functional and can change in terms of their structure. The same process, again, can be facilitated by iron 2 plus, 3 plus. All right, so focusing on that hydrogen extraction step, right? So this, you can think of it as an initiation step for the actual biomolecules. So the proton abstraction for a biological target transfers the radical onto that's present in the hydroxy radical to the target. So basically, now that radical is actually on a biomolecule, and so then organic radicals can even go on to react in with other reactive oxygen species, or even with reactive nitrogen species, producing other reactive nitrogen species. So this unstable modified biomolecule undergoes a series of reactions that can ultimately change its structure, can alter its function, and a long-term effect is cell death. So you can see this idea that complexation of those metals to those peptides can be quite dramatic in terms of really changing the molecular profile in the cells and leading to cell death, leading to the atrophy that you see in the brains of Alzheimer's disease patients. So the idea is that, as I mentioned to you previously, reactive oxygen species, reactive nitrogen species, we depend on our cells to survive. But one potential progression of the disease is that the rate of molecular damage from this oxidative stress is greater than the rate of repair, because we do have repair mechanisms available. And so that can lead to not necessarily the onset of Alzheimer's disease, particularly what I would say would be the onset of the basically the later stages of the disease, right? But I put a question mark because it's unclear in the where this falls in the chain of events. All right, so let's look at this question here, because there is a complexity here. How is it possible that uncontrolled ROS RNS formation by plaque leads to Alzheimer's disease onset or progression when plaque is external to neurons and the most damaging radical, the hydroxyl radical, cannot migrate very far before it reacts with something? So this is a question of, we have these plaque structures that are external to the cell, to the neurons, yet we're saying that that plaque can lead to the death of these cells due to the movement of these reactive oxygen species. But yet the distance between them is sufficient enough that in theory these radical species would not be able to reach the neuron target. So a possible thing that can happen is the following. In vitro reactions demonstrate that generated hydroxyl radical does not escape into solution. What that means is that basically these structures form the radicals, but basically they go on to react right within the actual structures, within the A beta peptide plaque. So you see damage caused to the peptide structures, but you don't see things being affected that are also in solution. But there is the possibility of the following, that perhaps you have oligomeric forms of the metallic peptides breaking off. And remember, these reactive oxygen species are, to an extent, destroying the structure of these peptides, of these aggregated peptides. It's possible that you can have part of that breaking off, and then there's a relocalization of that particular component that can become attached to the neurons, facilitating a direct contact with the generated radicals. So here I tried to give you a depiction of that, where you have a component of the plaque now localizing into parts of the neuron directly, so that you have an actual direct contact between the neuron and these metallated species that are redox active, right? So that is a proposal here that yes, the plaque may be external, but there is the possibility of a direct contact that can be facilitated between them. I mean, that's from the perspective of the plaque itself. But there are additional considerations. Because remember, this is not just a situation of the plaque formation. All right. Um, so here is another hypothesis that has to do with the plaque, where the formation of the A beta peptides that is proposed to be a part of the proteolytic degradation of the protein, the APP protein, that's a natural process. But what's happening is there's a loss of the actual clearance of these peptides, and so because these peptides are not getting essentially washed away, you're getting a buildup of these peptides, which results in a localized concentration, leading to these potential structures and the building up of the plaque. All right, so that is a sort of an additional hypothesis that may go parallel with what we have already mentioned about the self-aggregation of these peptides. All right, I don't necessarily see this as being independent of what we already talked about, because it just kind of gives you a scenario of how these peptides can come into proximity and favor the formation of these higher order structures, the fibrillation process, the formation of the plaque, even the metallation. But what we haven't mentioned, and I'm not going to go into any depth here, is that you also have these other structures that are actually on the neurons themselves, these insoluble neurofibrillary tangles, these NFTs, that can manifest due to the extensive fibrillation of the tau protein. So you have sort of a loss of the native state of the protein, leading to aggregation. And it has been observed that the NFTs, they can be comparable to the plaque in terms of their ability to interact, to bind to metal ions, and potentially facilitate these the redox active properties of those metal ions. And so again, when we're talking about redox active, we're talking about copper and iron. We're not talking about zinc. Zinc does not have that capacity to be redox active. Zinc plus does not have that capacity. All right. So what have been approaches, at least from the perspective of the metals, that people have tried in terms of the treatment of Alzheimer's disease? So you guys did your first assignment on getting some ideas about chelation therapy, and that has been invoked for Alzheimer's disease. So this idea of using chelators to detoxify the brain. All right, but you can imagine the complexities of that, right? Placing things into the brain environment, brain that's highly dependent on metals. So there are going to be some really stringent requirements for these chelator drugs. For instance, in terms of the delivery, the administration of these type of chelators. Well, you don't want to, let's imagine that you're imagining using chelators that are orally available, or maybe even inject into your bloodstream, right? Because the idea is that you're not going to administer directly into your brain. That's not a very feasible thing. Okay, so administering orally, you're going through your digestion of the compound, the metabolism, and then it being delivered into your blood, or direct administration to your blood, another possibility. But there are other possible administrations, but those are some realistic ones. All right, so in that context then, you want to use chelators that do not remove metals from transporter proteins. So as an example, you don't want to remove iron from serum transferrin, right? We know that is what we need to transport iron to our cells. You also don't want to remove you don't want to remove copper from ceruloplasmin. Remember, that's a really important copper transport protein, but that protein also helps to regulate the iron oxidation state that then makes the iron bioavailable to us. Another requirement is that these chelators must be able to cross the blood-brain barrier, right? So to be able to enter into the environment of the brain. So these are things to consider. But an extra layer here is this observation, where copper concentration, iron concentration, and zinc concentration are roughly the same in healthy and Alzheimer's disease brains. Roughly the same. So that seems a little bit, confusing. How is it that they're roughly the same? Well, apparently, what the issue may be is not so much the concentration levels, but rather the distribution of these metals. such that you get a distribution that is not normal, and then leads to sort of a loss of the functionality of these metals, possibly because of the coordination of the metals by the plaque, by the NFTs. And so what has been observed is that you do have high concentration of metals in these structures, right? Um, so that's something to address, that you have a loss of that of the sort of the homeostatic biodistribution of the metals in the brains. All right, so adding to that then is another requirement, that the chelator must have intermediate affinity to remove the metal ions from the plaques and NFTs, but not from the important metal storage sites. Okay, we're talking about things now with regards to the neurons themselves. We're not talking about the transport from the blood into the brain. Now we're really focusing on the neurons. So we have to have a chelator that has strong enough capacity to bind the metals, but not to remove the metals from the storage in metallothionein. So we briefly talked about metallothioneins in our very first set of lectures, and ferritin, which is, as we've talked about, storage of iron. So metallothionein, storage of copper and zinc. All right, so that's something that you have to have a really good control of that of the affinity of the chelators. Then the chelator could be cleared from the brain and thus remove the metal ions, but maybe that is not so important because, again, you have a loss of the metal distribution. So clearing the metals is not necessarily a good end goal, but perhaps at least temporarily you remove it will remain in the cells, maintaining the metal pool unavailable to the extent that it can't necessarily rebind to the plaques, to the NFTs. But perhaps there's the possibilities to relocate that metal, to redistribute it. That might be complicated, but there could be that possibility. All right, so we're going to look at a few chelator examples. So here we're looking at cleoquinol, abbreviated CQ. So this is the parent ligand, and to the right is a derivative of the ligand, this PBT2. So in terms of the coordinating moieties, here highlighted in red, where it has the capacity for metal coordination. All right, so initially, cleoquinol was developed to treat the human intestinal amoebiasis, which is a disease caused by the amoeba, it's a parasite, this entamoeba histolytica. So that was its original purpose. But a lot of drugs are repurposed for the you understand the chemical property or the biochemical properties of a drug, and you try to take advantage of it since it already has passed clinical trials. So you already have a sense of its toxicological profile. So you try to exploit that to then see, well, what other things can this potential drug be able to treat? So cleoquinol was, because it does have metal binding capacity, well, it was thought to, well, let's go ahead and see if it can actually be used for the treatment of Alzheimer's disease. So it actually reached phase 2 clinical trials, but it was stopped, and it was stopped because of the major impurities from the diiodoform of this compound, right? So I guess by diodom, perhaps it could be that you have the two, instead of the chlorine and the iodine, you have both of them being iodine. All right, and perhaps that particular impurity was not efficacious, or simply that there was just not good quality control of the material. So the derivative on the right was actually tested. So it was synthesized sort of as a response to this other, the parent compound not succeeding, was advanced to phase 2 trials, but did not succeed to an extent because of insufficient efficacy. Okay. But let's get a little bit of a perspective of how it can coordinate metals. So here we're looking at the coordination of copper. So this gives us a perspective, looks like something that's characteristic of square planar coordination number 4. And the orientation of the bidentate ligand. Here we have the coordination of the ligand to zinc 2+. So the structure that we see here is characteristic of a trigonal bipyramidal structure. Okay, so in terms of trying to get a sense of the formation constant, so in medium, mimicking brain fluid, the beta values for the copper complex, the copper with the two CQ ligands, is a 1.2 times 10 to the 10, whereas the zinc compound, okay, has a beta value of 17 times 10 to the 8th. Okay. So how might this ligand operate? We know that its potential for clinical application is no longer, but some of the insight that has been obtained. Well, it was observed that the copper affinity of the ligand is lower than that of the brain plaque. So brain plaque apparently has a much higher affinity for the copper. So perhaps the cleoquinol can serve as an ionophore to transport free copper 2 plus to neurons to try to restore the copper homeostasis or the copper distribution and restore proper function. So the idea is that perhaps the cleoquinol is not necessarily pulling copper from the brain plaque, but at least trying to help with the redistribution of copper. So that wouldn't necessarily address the main problem, but it is addressing sort of the one of the byproducts or one of the side effects of this condition. Okay, so it has also been observed that perhaps this molecule may be operating not because of its metal binding capacity, but instead it may operate by blocking the ability of the A beta peptides to self associate. So it may be doing this exhibiting this property either by directly interacting with the A beta peptides, or maybe in some way maybe it is related to its metal binding, and because it can bind metals, it can prevent the self-association. So it's a little bit unclear how this is being observed or manifested. But anyways, association complexes with the A beta peptides inhibits oligomerization. So these studies have observed that an interaction between the CQ and the A beta peptides results in the prevention of the higher order structures, the oligomerization. All right, let's look at another chelator. So here we're focusing on ferroprone, okay? And so, as the name implies, it is an iron chelator. The left, I show you the ligand and the coordinating moieties, okay? And on the right, I show you the potential structure that this bidentate ligand can form. Here we're looking at the ligand deprotonated. You have three equivalents of the ligand surrounding the metal center, forming this type of octahedral or distorted octahedral structure. So deferriprone is a well-known drug used for treating iron overload, especially in the genetic disease, the beta thalassemia. It forms that structure, or at least that proposed structure to the right, as this octahedral tris bidentate complex. And it's been observed that the iron 3 complex can cross the blood-brain barrier. So additional properties that have been observed for the ligand, it can decrease the amounts of A beta 40, A beta 42, the amounts that are actually observed, and even the beta secretase, which cleaves the A beta peptides from the APP protein. And this has been observed in vivo studies with rabbits that have an Alzheimer's disease-like condition. All right, so here, for whatever reason, that molecule has the capacity of inhibiting the enzyme that's contributing to the formation of the peptide. So this may not necessarily have to do with the metal binding capacity of the molecule. It's also been observed that it can block the phosphorylation or the extensive phosphorylation of the tau protein and prevent the NFT oligomerization, so the formation of those structures. But what was also observed in these in vivo studies was that it could not prevent ROS generation, okay, and possibly because of some potential pre-binding to metals, and therefore is unable to scavenge the metals that are already bound to plaque. All right, so this is similar to the cleoquinol, where perhaps it can bind metals, let's say from the blood, and then deliver into the brain to redistribute the metal. So perhaps here, because the ligand has the capacity to bind iron quite strongly, it may come into the brain already iron bound. So A strategy that was proposed to overcome the potential pre-binding of iron to this chelator was to invoke the use of a pre-chelator version of DFP. All right, so I know that Daniela last semester did a presentation on prochelator, so she could probably give us a talk about this concept. I'm going to just briefly summarize here. So a prochelator is a version of of a chelating molecule where you have put on a component to block its metal binding capacity, but you have put on something that within the biological environment, um, something within that environment can cleave that blocking group and then activate the chelation component of the molecule. So that's what a prochelator is. So so in this structure, so this is the ferroprone over here, okay? What we're seeing is that this protecting group has been added on to one of the coordinating moieties, right? So it's no longer able to be a bidentate ligand. So it's basically you have removed that capacity, that chelation capacity. And so this group that's here, you recognize that that molecule is a sugar bound and serving as a blocking group. But there was another thing that was added, this thing that's highlighted in yellow, this targeting group, all right? And we're going to see what about that group is important. All right, so let's look at the components. So it contains, in green, as highlighted in green, a glucose protecting group to block metal binding. So what happens is then the molecule is able to cross the blood-brain barrier without metal binding. Then the glucose protecting group is removed by the beta glucosidase enzymes, which are abundant in the brain. So you're exploiting the presence of these enzymes in the brain to basically then cleave, okay, the prochelator, and that would now convert it into a chelator. But then we have this other group here, and so here it's called the targeting group. Well, what exactly is that? So here, this molecule has a thioflavin T targeting group, which has an affinity for the plaque. So something about that structure enables it to interact with the plaque. And so that serves as a targeting group, or a group that will allow for the whole molecule to have an affinity for the plaque. So you can imagine you lose the sugar, and now this group is going to lead the molecule to the plaque, right? And so the plaque is metallated, and that's going to then facilitate the chelation of the metals from the plaque to then now decrease the generation of reactive oxygen species. What is going that those species that induce oxidative stress and potentially then leads to cell death, right, in the progression of this disease. So that was a proposed structure for trying to overcome some of the potential limitations of just the parent chelator. Because remember, that chelator was designed as an iron chelator, right, to address iron overload. So you can imagine that in its transport from its route of an administration to its target site, which in this case would be the brain, right? You have to think about how it can be biotransformed. So biotransformed in the sense that it can become metallated. And so these are things that you can try to do to minimize the metal binding capacity of the molecule while also improving its ability to interact with plaque. Okay. All right. So these are just an overview of efforts that people have done to try to combat at least some of the symptoms of Alzheimer's disease. It may not necessarily be at the root of what is, causing the disease, but it is an approach that can be done to try to handle its progression. Right. So, any questions from you guys about this material? Any doubts?
I have a question.
Go, Adriana.
When like the molecule that is not like the precursor, the last one we saw, the one
Yes.
that binds the iron, is it like dye sensitive or
Mm-hmm.
also like the proculator or not?
Right. So I believe that so that was added in to be able to track it. So to be able to see if it can actually locate to the plaque. So that was that component of of this group, which is also a dye. So you're saying, is
But
it
the
sensitive? Uh-huh.
the first one, the one that's not the prochelator, is it also tracked with dye or not?
So this group here, I don't think it has any capacity to be fluorescent. I could be wrong, but it doesn't have enough of the, I would say, aromaticity that I would think you would be able to easily track it. I could be wrong, so I would have to look up the literature. But typically, people will try to use the fluorescent property of a molecule to be able to track it. And so I don't think that there is enough there to be able to track that one directly. But I can
And
look that up to
like,
see.
how do they actually track it? Like, I don't know if I lost that in the explanation, but do they actually track it to know
No,
it
they
reached
didn't. They
the?
didn't track it. Most things are not actually tracked because they're not very easy to do so. So typically, what you do is you look for some sort of physiological response. So oftentimes, for instance, when you do cell work, you're not necessarily tracking what your molecule where it's going, because oftentimes you have to add some sort of reporter group, right? Something that's fluorescent or something that's luminescent, something that will help you to get a sense of where it's going. But then you have to think about the addition of a group like that might compromise a small molecule because you might change some of its properties. So it's not so easy as just adding a group. You have to kind of do some additional assays to make sure that you have not, changed the actual mechanism of action of that molecule. So no, I didn't report anything about it being tracked. What I was reporting to you was potential observations of what was happening in terms of the generation of the antioxidant species. Was that inhibited? No. What they observed in those studies with the rabbits was that it was not inhibited. So that was an assay that was done to, and these are things that you can do with cells to be able to see if you have inhibited the formation of those type of species. Does that address your question?
Yeah, thank you. I was just thinking, like,
Mm-hmm.
how do they actually know which one reaches, like, in greater concentrations, the target molecules and tissues? So, yeah.
Right. So I would say it's not so easy to know that. You have to monitor the effect. And so oftentimes you really can't necessarily do this on human beings, right? So they're often done with animal models to try to get a sense of like, how is that impacting the plaque formation, or excuse me, the amount of plaques that were present before and after treatment, things like that. So these are not very easy experiments to do. But the tools that are available with what capabilities that we have can help to address that. So magnetic resonance can be helpful in that regard. And some of these things we're going to look at later in the course, tools that can help you to, assess a disease. Okay.
Thank you.
You're welcome. Other questions? All right, everyone. Well, I will see you on Thursday. Take care.
Profesor,
Yeah, what's up?
¿puedo hacerle una pregunta luego de que se termine la clase?